This is the second video for section 8.1, where we will actually look at integrating some of the different techniques that we mentioned. So one of the techniques that I gave in the last video was substitution. Okay, so substitution again is something that you are already familiar with because we've had to use it. We've had to use it on the last exam. We've had to use it throughout homework. But let's say our first example is to integrate dx over 3 minus 5x to the 4th power. So what I want to do is let u equal some expression, and in this case 3 minus 5x is the best choice. I also want to find the derivative of that, which would be negative 5 dx. Now when I go to make substitutions here, you can see that 3 minus 5 becomes u, and I have u to the 4th. But the problem is that I need to substitute in dx, and what I have is negative 5 dx. So I need to make an adjustment of dividing both sides by negative 5 so that I solve for dx in terms of du. So instead of dx, I'm going to write negative 1/5 du. Now another equivalent way of writing that is to pull out that constant multiple of negative 1/5, and then I have 1 over u to the 4th du that I'm integrating. Or you could equivalently write that with a negative power, which does lead to the integration process a little bit better. So what I'm going to do here is add 1 to the power, divide by that power, multiply by the constant, and then of course we can't forget to add c. So cleaning that up, a negative here times a negative down here will give me a positive, and then I'll have 1/15 u to the negative 3 plus c. Notice I left a big blank for u, and that's because I need to plug it back in, resubstitute. Remember, when you're dealing with a definite integral, you don't need to resubstitute because you just changed the limits of integration to reflect that substitution. But with an indefinite integral, you have to resubstitute in the end. So that would be one form of the answer there that would be acceptable. Okay. Here's another example where we're going to use substitution. So we have cosine to the 4th power of x divided by sine to the 6th power of x dx that we are integrating. So we need to think about a substitution here, although it's not incredibly obvious that substitution will work. Think about if you let u equal sine to the 6th power, you're going to get some sort of sine to the 5th power along with some other things. And then if you get cosine, or if you let u equal cosine to the 4th, you're going to get some cosine to the 3rd power with some other things. So the bottom line is if you try to substitute right here and now, you're probably going to get stuck. So one option is to take what's given, the integrand, and rewrite it in some way that allows for a more obvious substitution. So you can kind of play around with this. You may not know exactly the best way to rewrite this at first. Try a couple different things. But one option is to think about having cosine over sine, and that being cotangent. So if I think about this as cosine to the fourth over sine to the fourth times 1 over sine squared, that would equivalently represent what I was given. So again, this looks like a 4x, that's a power of 4. But all of this is cotangent to the fourth. And then think about this right here as being cosecant squared. Alright, so if I rewrite it, let's see if substitution will work for me. So one thing that I'm going to try is I'm going to try letting u equal the cotangent of x. And the reason that I did that is because I know that its derivative is negative cosecant squared. Negative cosecant squared. So that makes things kind of nice. What I have now when I substitute, instead of the cotangent of x to the fourth, I have u to the fourth. And then instead of cosecant squared x dx, I can actually substitute negative du. And again, I had this extra negative sign in here, so I just need to account for it by dividing both sides by -1. Alright, so I can pull that negative out front, and then I can integrate once again. So if I add 1 to the power, that'll be u to the fifth over 5 multiplied by the constant and add c. Let's reintroduce what we substituted. And here's one form of the answer that would be acceptable. Typically this 5 here would be written on the inside, but it means the same thing. Alright, so there are two examples of substitution. One example, you had to rewrite what was given first and then do a substitution. So that is in the textbook referred to as subtle substitution. So you can't see the substitution right away, but if you play around with it a bit, you might recognize the fact that substitution will work for you. Alright, let's keep it going here. More examples. So in addition to substitution, we had a bunch of other algebraic techniques that we could utilize. The next example that I'm going to show is going to address splitting up fractions. So this will be example 3. And I'd like to integrate the fraction x plus 2 over x squared plus 4 with respect to x. Alright, so splitting up the fractions, what I can do is I can take x and divide it by the denominator, and then I can add that to 2, also divided by that same denominator. So just a quick check to make sure that mathematically or algebraically that's a sound move. You can think about what would happen if you were to take these two fractions and try to add them back together. Would you get what you started with? And if they have a common denominator, then we go ahead and just add the two numerators, and yes, in fact, we would get exactly the same thing we started with. So again, we're undoing common denominators here. And so let's hope that that makes this integration doable. Now, I'm actually going to write it as two separate integrations, although that does not need to happen. Rules of integration from Calc 1 say that you can integrate a sum as one integration, or you can split it up and make it two separate integrations. Alright, looking at this, let's focus on this one right here for now. I'm going to use a u substitution. I'm going to let u equal x squared plus 4. which leads me to du being 2x dx. I only have a 1x dx, so I'm going to divide by 2 to make that adjustment. Okay, now I can resubstitute so that I'm integrating 1 over u du times that constant multiple of 1/2. Okay, this came up in last week's discussion, where if you're integrating u to the -1 power specifically, not any other power, but only the -1 power, it has its own special rule. And that rule is that it integrates to be the natural log. So we'll have the natural log of the absolute value of u plus c, except that we have to resubstitute whatever it was that we let u equal, which was x squared plus 4. Okay, so that is the result of only this first term that we had in our expression being integrated. So we have to also integrate the other piece, and then we have to add those two results together to get one big final answer. So looking at this other term, we actually have something completely different going on. And if you have one of the derivative integration formula sheets that I gave you throughout the chapter 6 that we first studied, then you might want to refer to it in order to integrate this one. So here we have 2 times 1 over x squared plus 4 dx. And 1 over x squared plus 4 kind of follows a specific format of a specific integral. And so again, if you're looking at your formula sheet, you're going to notice that when you integrate inverse tangent of x, that the format is similar to what you're seeing here. So you're going to get 1 over x squared plus 1 when you integrate that. So we can make that work here. We just have to make a slight adjustment because we have a constant of 4 as opposed to a constant of 1. And one thing that you might want to remember is that this 1 actually comes from a constant being squared. This is actually 1 squared. So when we make our adjustment here in the argument of the inverse tangent, we're actually going to think about the number 2 and not the number 4, because 2 is actually squared to get 4. So all of this becomes the inverse tangent of x over 2. And then what we need to do is we need to multiply that by 1/2 according to the chain rule, or the opposite of the chain rule in this case. So don't forget to bring down this multiple of 2. And what we end up with is the inverse tangent of x over 2 plus c. So if you're not totally convinced that this is the result of integrating this expression, then you might want to go to your formula sheet and try to take the derivative of this and verify that it does in fact give you this expression. So we can check our work. It's a little bit tricky because it does involve simplifying a complex fraction, but hopefully you can convince yourself that this is correct, and if not, it's something that we can always address in the discussion. But anyway, it becomes the second term of my answer, and so I've got 2 terms. I don't need to add c twice, so I can just write all of this one time, or I can write all of this and then write c once at the end.